All right, get started in a minute. All right, so welcome. We are in discussion 12. Today we don't have a handout because we are going to talk about the midterm because we didn't really cover anything new last week. So there's no, I mean, it's only on Tuesday, so there's no need to really talk about this week actually. So we thought cover the solutions. Most of you have already done pretty well, so might not be super useful, but if you still have any questions, let me know. You should be able to see your base for the midterm on Blackboard. If not, then let me know. There is a lot of pending material on my side, and I sincerely apologize for that because I was super busy in the last 3 weeks for finishing up my dissertation, and hence didn't get time to grade. But I'll finish everything by the end of this week, so you'll have your R project, your homeworks, and your quiz solutions, quiz grades on Blackboard by the end of this week. Okay. All right. So before we proceed, any questions about anything? Okay. In that case, I'm going to switch off my camera and share my screen, and we'll go over the solutions together. All right. Okay. So we can start with the first problem. And the first problem was, I think most of you, I think actually probably all of you got it right. It's a very simple problem. And this problem essentially the first problem that is, so what's given to you is you're given two columns. One is essentially the protein concentration of patients who have a heart disease, and the other one is about patients who do not have a heart disease. The first question that you're asked is this a paired sample or an unpaired sample, right? And it's a very simple problem. The reason, I'll probably write this down here. This is unpaired is you can run it in two ways. And the first way is that you cannot have heart disease, not have a heart disease. And the other way is you're kind of given that these are 5 different people, okay? So given this information explicitly, so it's unpaired. Okay, we move on to the second problem, which essentially asks us is the QQ plots are given, and the problem asks us, can you really do a t-test? So the only thing that we need to really verify that is whether the conditions for a t-test are satisfied, and t-test is a valid test if you have enough sample size. Now this enough is a broad term. We'll go into that detail a bit later. The other thing is normality and simple random sample, right? So normality should be satisfied for both these groups. So this is okay, but this is not normal. And it's not normal because this particular point is deviating away a lot from your designated QQ line. Okay. The other thing is it's also like 5 samples is like a very small sample size to really do a t-test. Okay. And hence we can't do a t-test. Okay. And that's because, and one of the reasons is because this particular column is not normal. Okay. So we are unpaired and we cannot do a test. So the only test that the choice of test that we are left with is the Gaussian man. So what's our null hypothesis? The null is the protein concentration is same for hard. Okay, and this is like one generic way of writing this. And the alternate is we want to be directional, and what is the direction we're interested in? So we're interested in this direction that people with heart disease have lower concentration of protein. Okay, so protein concentration is lower in the heart disease. Okay, so it's a very generic way to write it. It's not, there's no hard and fast rule of writing these hypotheses, but as long as you convey the idea, it's fine. Okay. Next thing we have to do is calculate the p-value. And for that, we need to carry out the Wilcoxon test. And the way we do that is we need to count the number of heart, which are, so writing heart generally to mean that it's a heart disease column, and this one is non-heart. Okay. So for this particular column, the heart smaller, I'm going to count for each value on the row, how many number of observations are below this, right? So this is 5, 10 is 7 and 9, so that's 3. 75 is all of them, 8 is 2 and 7, and 400 is all of them again. Okay, and the sum total for this will be 20. We do the same exercise on this side. So 20, so the only two observations are 8 and 10. 16, 8 and 10 again, 2, 0, 7, 0 again, 9, 8 only, okay, and this is 5. So we need to check if these values make sense, and the way to check that out is to make sure that these two sum is equal to the product of the sample size, okay? Okay, some of you, I think, did a mistake here. Actually not in this part, but the same part. So the statistic that we have is max of 3 and 5, right? That's 20. Our n and n prime are 5. So we'll go to the table at the bottom on the non-routine test problem, and we'll select the row corresponding to 20. Okay. One other thing that you need to be about is the non-directional. It's this particular is non-directional, right? So you need to divide it by 2. Okay. So the p-value that we get is 151 by 2. Okay. And the next thing that we want to ask ourselves is what is the conclusion of this, right? And the conclusion for this is based on alpha equal to 0.05, which is definitely smaller than 0.075, right? This is what 0.075 is. Okay, question, let's see. Okay, so my audio seems to be having an issue. Okay, actually this issue yesterday also. I don't know what the issue is. Let's see what if I can change anything. Hold on. Is this any better now? Okay, let's hope it remains so. Okay. I'm really sorry. I'll need to figure this out why this problem is new. Okay. All right. So we get this particular value of so what we're doing is we were still want to conclude what is our conclusion, right? So your P is greater than alpha, and hence we fail to reject the null. Okay. In the second part, we are still going to do the same problem, but now we have removed this particular observation, the 400th, the value which was kind of an outlier. Okay, so the new data that you have is H, and in H, we have 20, we have 16, 2, 7, and 9, we have 50, 10, 75, and 8. Okay, We're going to count the number of hard samples which are smaller, the number of non-hard samples which are smaller. Okay, and this is 5, this is 3, this is 5 again, this is 2. So this sums up to 15, and these values here essentially remain the same. Okay, so our W statistic now is 15 because it's the maximum of 15 and 5. Your N is 5, your N prime is 4. Okay, so we go back again to the same table and do the same thing at this particular value, right? So if you notice, there is no value for 15, it's 0.191. So the only thing that we can conclude from that particular table is that P is definitely greater than 191 by 2. Okay, and this implies that P is greater than alpha. So we fail to reject again, and hence there is no change in conclusion. Okay. Part F, we are asked is what condition should you verify before doing the test in part D? So one thing is they should definitely check for both of these groups being simple random samples. And the other thing is of independence. Okay. And why independence of these two columns? So since you're doing an unpaired t-test, it is assumed that there is no relation, right? So these two columns need to be independent. Okay, which is not the case if there is a paired testing that's being done. So in paired testing, this one particular row is kind of dependent, right? Each row is dependent because you're testing it on the same patient, which is not the case with unpaired testing. Okay. Okay, just curious, is my audio still noisy? You can let me know in chat. Okay, it's much better. Okay, that sounds good. Okay, all right, so we'll move on to problem 2. And problem 2 is in a particular clinical setting again. You're essentially trying to test whether or not a weight loss drug has an effect on the patient's cholesterol level. Okay, and you're given this data across 5 patients. You're given that the sample size is just 5. And this is, the first problem is it a paired or unpaired sample? So this is pretty easy. Each of this patient is being tested 2 times, one with the treatment, one without the treatment, and hence it's a paired setting. Paired setting, right? The next question is do the t-test. So it explicitly asks you to do the t-test, but you have to choose between paired versus unpaired, right? And since we have already chosen this option to be paired, then we are going to do a paired t-test. So before we do that, we'll state the null. And the null is that there is no difference in the cholesterol levels. Sorry. I'm just going to write between the two groups. And the alternate is that there is some difference. Okay. We're going to bound the p-values. So in order to calculate the p-value, we are going to do a t-test. Okay. And the first thing, actually, some of you ended up doing, figuring out that you have to, so the t-test is given. This is paired, but some of you did a mistake at calculating the actual p-value. And most of this arises because of the fact that you use the wrong version of the standard error formula. So notice that this is a paired setting, right? And the moment you see a paired setting, you work in a different domain, and you work in this domain of differences. Okay, and I'm going to call it before minus after. It doesn't really matter whether it's after minus before, before minus after. You can pick up any direction, but you have to stick to it. So this difference is minus 10, minus 40, 5, minus 15, and minus 15. Okay, so d bar is minus 10 minus 40 plus 5 minus 15 minus 15. If you calculate this, you get minus 15. Okay, so far it's straightforward. Okay, no issues there. You could get the same difference value by actually subtracting the mean of these two columns as well. It's essentially the same thing. The fact that the thing that we actually need is the standard deviation of d, which is given by di minus d bar, okay, and minus 1 square root of this, right? So if you calculate this particular value, this value is essentially going to be 16.2. Okay, and notice what uh, so what's not right about this particular problem, if you do it the wrong way, is so if this was in a unpaired setting, then your STD is given by this formula. Okay, you can't use this for uh, this particular problem, right? It's because we are working in the paired domain. Okay, but you still get partial credits for that. So if you use the wrong formula, it still give you partial credits, but that's just make sure you understand it's not the right approach. We get the standard error again by the same formula. So 16.2 divided by root 5, and that comes around to be around 7.245. The next thing is our t statistic. The t statistic is given by this value. Okay, and if you substitute all the values, you'll get a value which is minus 2.07. Okay, notice that I'm getting a negative value here, which is perfectly fine. There's nothing wrong about it. The degrees of freedom is 4. It's 5 minus 1. So in order to calculate the p-value, I'll go to the t table. I'll go to the row, which is df equal to 4. I look for a value of 2.07, which seems to be lying between this. Okay, I'm looking for the absolute value of the t statistic. Okay, that's just because this table is giving you the right half of it. Okay, which is essentially the positive value. So this is, first of all, it's directional. So p is 0.1 times 0.05, but you can't really stop there. You need to multiply this p-value by 2 because we are working in a non-directional alternative. Okay, so your p-value is 0.1, 0.05. This divide times 2, so your p-value is, okay, and in whatever world you are, alpha, this is definitely greater than less than alpha 0. So p is definitely greater than alpha, and that you can conclude that you will fail to reject the null. Okay. Next problem is simple. All you have to do is calculate the standard error, the confidence interval, and that is given by, let me write this down clearly. So t 0.0258 standard error of t. Okay, and the only thing that we really need to calculate, and I think some of you did a mistake here, is to get the t statistic. Okay, so this is t statistic. This is not 1.96. This is not your standard 95% infant. That 1.96 actually arises because if you're working in the z domain, but you're not. You're working in the t domain, right? So you're working with the t distribution. So you have to explicitly calculate this value. And this value will come from, again, from this table. So it's slightly more useful if you actually go to the bottom part of it and read it. So you have the 95% confidence level, your degrees of freedom of 4. So your t value is 2.776. Okay, and some of you got the wrong value here, but this is what should have got. Okay, and if you plug in all the numbers, you already have SE and you already have D bar. If you plug in the numbers, this will be minus 36.1149 and 5.1148. Okay, and 0 is contained here. This is just a sanity check because these two should conform to each other. Okay. Okay. Any questions? Think we're left with very few people, but thank you for sticking around. I actually kind of miss teaching in person because this particular mechanism has no feedback at all. So I have absolutely no idea if what I'm talking about is making sense, it's being understood. But if you have any questions, please feel free to stop me, okay? Or please feel free to message me. Okay, so we'll move on to problem 3. And problem 3 is giving you experiment from genetics where there are 3 choices. You get either black eye, the children could have white eyes, or the children could have red eyes. Okay, and in this particular experiment, the Tom has got 40 children total. Okay, and given that you have seen a total of 40 and you have a 25% chance of being black eyes, the expected value that we have here, so make it clearer. So this is blue, white, and red, and these are your expected. Okay, so this is 1/4 of 40, which is 10. This is 1/2 of 40, which is 20. This is 1/4 of 40 again, which is 10. What you're observing is 8 for this, 22 for this, and 10 for this. Okay. What is it we are interested in? We are interested in the null hypothesis, which the null hypothesis is that there is no, essentially there is no association. There's no difference between there is no association between the genetics that you're seeing and what your expectation is. So the choice of association will be your chi-square statistic. Okay, and let me write this down. So if you put in the values here, this is a very simple number to calculate. This value comes around to be 0.6. Okay. So the degrees of freedom that we have is 3 minus 1, which is 2. So if you go to the chi-square table, look for degrees 2. 0.6 is definitely not lying anywhere here. So P is greater than 0.6. This is already non-directional, so we are okay there. And so this is omnidirectional. Okay, so P is definitely greater than 0.2, and hence we will fail to reject. Okay, all right. Second problem, again, it's a simple problem. All you had to really understand was what is it talking about in terms of 800 students. So what happened is you have a class of, let's say, 800 students, and 38 of these students ended up rejecting the null hypothesis, right? And the question is kind of trying to ask you, what is so special about these 38? Have they done some sort of error? Because around 720 of them are not seeing any change at all, right? So just by going by the numbers, then it seems odd that only 40% or 38 of them are actually seeing something which is different from the remaining 750 or so. So what really is going on, right? So probability of probability of a false positive, if you're doing one test, is equal to your level of significance, right? So if you just do one test, there is a 5% chance that you will falsely reject the null hypothesis, even though it's actually true. Hence, it's called a false positive. Okay. Now, if you're doing 800 tests, so in essence, you expect that you will end up rejecting 40 hypotheses, even if they're actually true. Okay. And this, in a sense, is how the testing is set, right? This is kind of a trade-off that you make. So you're seeing 38 of them. So there's no surprise, right? There's no surprise. Just because this is our expectation of around 40 of them actually doing an error. Okay. Is that clear? So they did not do any mistake. It's a false positive. Okay. All right, we move on to problem 4. Problem 4 is again a simple problem. You're given this data coming from association between a drug D and a mutation M. I'll first write down the totals for each row and column. This is 100, this is 400, this is 280, this is 220. Okay, I think all of you got this problem right. What is the probability that D is effective given that a patient has mutation M? So it's a very simple conditional probability problem, which now all of you are experts at, right? So we have 80 and we have this to be 100. So this is 0.8. We do the same problem between D and MC. So we have D, MC is M complement, which essentially means this. So this is MC and this is M. Okay. Sorry, this should be 200. So this is 0.5. Simple problem, no surprises there and nothing complicated. Okay, so far. Okay, fine. So now we are interested in the null hypothesis and the non-directional alternative, right? So what's the null? The null is also simple. There is no association between drug D and, again, there are multiple ways to write the statement. As long as you imply the idea, it's fine. Okay. Okay, you can say the same thing in terms of independence. You can say the same thing in terms of conditional probability. Everything is fine. Okay, bound the p-value, right? So we have to do a test, and the choice of test for association is a chi-square. And in order to calculate this chi-square, we need the expected values. So if this is your mutation M, this is your MC, this is your D, and this is your DC, the expected value is given by, sorry, yeah. Okay, so how did we get this particular expected value? So we have 500 people in total. 100 of them have a mutation M, and 80 of them seem to have a disease D and mutation M. So in a sense, sorry, this is wrong. It should be 280. Okay, so we have a total of 100 people who have a mutation M and a total of 280 people who have a mutation D. Who are taking drug D, where the drug D is effective. Hence, by chance, you expect 280 times 100 divided by 500. So 100 by 500 is the probability of someone having a mutation M, and you're seeing 280 of them of the patients which have drug D effective. So expected number of people who have M and D is given by this particular value. Okay, and if I did my calculations, we look up the, I think this is 56, if I'm not wrong. Yeah, I think it's, so this round comes around to 56. Okay, similarly for DC, this value is going to be 220 times 400, 220 times 100 by 500. And I think this comes around to 40, I think 224. Okay, and I think this value is, let's see, this value I think is 44, and this value is probably 176. Okay. Let's see. Yeah, I think that's, no, sorry, this is wrong. This is 44 and this is 224. Sorry. Okay, I'm going to do the same calculation. So this is just, the solutions are already up, but this is what you get. So you get the chi-square value for this by doing this summation. Yeah, one quick check would have been to just add these two values, because these two values should add up to 280, right? And similarly for these two, they should add up to 220. So this is right. So we get, so simple, you can have a calculator. This value is around 29, and the degrees of freedom are 2 minus 1 times 2 minus 1, very small. Actually, to be honest, you don't even have to look up the t-table, the chi-square table. This value is by itself very large for a degrees of freedom 1, because most of the values are in single digits generally. So a p-value is definitely lesser than 0.001, and hence you reject the null. Okay. All right. We'll move to the problem 8, problem 5. Problem 5 essentially was a collection of 3 problems which kind of tested you on your understanding of the interpretation of p-values and association and simple random samples. The first value is the first problem is very simple. So you have 20 patients in one test, you have 150 patients in the other. In one of the tests, you're getting a p-value of 0.25. In the other one, you're getting a p-value of 0.002. So what really is going on, right? So one of these tests is showing you significance, the other one is not. The one that's showing you significant has 150 patients. The one that's not, it has only 20 patients, right? So the difference is coming because your standard error is smaller for large sample sizes. So there's nothing wrong with doing the first experiment. It's just that uh, since the sample size is small, your p-value is not significant. Okay, but if you sample more patients and there is an effect size, there is some effect, then the p-value has a higher probability of being significant just because of the virtue of your sample size, right? And so the second p-value is smaller because of large sample size. Okay. Okay, we'll move to problem B. Problem B was one problem which I saw people writing a lot of stuff. So one thing about statistics is literally your answer can literally end up in 2 lines. You don't have to be verbose, okay? So if you're being verbose, probably doing something wrong. So in order to just explain this, right? So what's really going on? So this person has done an experiment, and the way she has done is she has observed these patients. So it's an observational study who have taken drug A for several years, and they are much more likely to develop dementia than the patients who have taken some other drug over different years. So the person examines all these patient records and does a statistical test and is able to reject the null hypothesis that whether or not her patient gets dementia is independent of the whether the person takes drug A or drug B, right? So it's an observational study. But the problem with this study is this is not a simple random sample, right? So it's not a simple random sample, and hence the conclusions cannot hold or are not generalizable, right, to the population. What do I mean by that? So first of all, this is an observational study, so there's nothing really under control. It's more of an observation. And the observation is that there is independence between the person getting developing dementia based on drug A or drug B. So there are some confounding variables hidden there, which have not been talked about. So people who are taking drug A are, for example, it's the cheapest option for them. So there is some sort of economical confounding that's happening, economical background confounding that's happening there, right? So it's not a simple random sample, and hence any conclusion that you draw, the reason that this is not generalizable is because you're drawing a conclusion at the global population level, whereas the sampling that you're doing is not a simple random sample, and hence you cannot really extrapolate this conclusion to a general population. Okay. So all that I was looking for is whether you are able to figure out whether this is a simple random sample or not. Okay. The once you figure that out, there's no other explanation required. Okay. We move on to the final problem, and the final problem also is one which I think some of you ended up getting it wrong. So the problem talks about doing 2 different hypotheses tests. One test is based on the height and the other test is based on sugar concentration. And the final conclusion is like one of the p-values is 0.93, the other one p-value is 0.31. So the farmer is concluding that there is probably more evidence to support the statement that the mean heights are the same than there is to support the statement that the mean sugar concentrations are the same. Now, the moment you read this statement, and if you remember the explanation of the p-value, this should kind of sound a bit strange because this interpretation. So this interpretation of p-value is incorrect. P-value is not equal to the probability of. So it's not a probability of the null being true. Okay, it's the probability of seeing something as extreme that you're seeing, given that the null is true. So comparing these two evidences just based on their p-values is meaningless. Okay, does that make sense? So remember the p-value interpretation, that's p-value is equal to probability of seeing a statistic at least as extreme if the null is true, right? So you're already assuming that the null is true. So you cannot really claim that if you get a higher p-value, then that particular null has a higher likelihood of being true. Okay, that's not what is being concluded from this study. Okay, so we are done early. I'll take any questions you have. You can also go through your exams and let me know if you have any questions. I've given you comments about, let me switch this on. So I've given you comments about each of these problems, and if you do not see any comment, that means you got full points over there. For wherever I've left a comment, that means I would have also indicated how many points you lose there. Okay. If there are any calculation mistakes or anything that I missed out, please let me know, and I'm happy to take care of that. Since we have more time, I'll just talk about one particular announcement that I should have made earlier is about project 2. So Peter has already put out project 2, and I'm lagging behind in grading a project 1, but it should be done by the end of this week. So project 2, in some sense, is different from project 1. In project 2, you're going to work with your own data sets. So you'll have sometime around 2 weeks, around 10 days now, to decide what is the data set that you're going to work with. And this choice of data set should be such that you can run an ANOVA analysis on that. Okay. So, or ANOVA or linear regression. So if you can run ANOVA, in most cases, you can also run a linear regression. So you've already been taught one part of ANOVA. Peter will give you more examples on ANOVA analysis in tomorrow's lecture. So in this time, meanwhile, you can start thinking about what data sets have you come across? What is it something that you can run an ANOVA on? So some quick examples could be looking at genetic data sets, looking at, let's say, influenza versus the number of influenza cases detected versus number of some other disease cases detected in a particular short span of time or over a particular period of time. Okay, so start looking for those data sets. I think Peter has also given you some pointers about where to look at. So those sources have good data sets. The project 2 is going to be slightly simpler. The problems are very broad overall. All you have to do is to be able to run ANOVA and linear regression on those data sets that you choose and draw some conclusions. Okay. And we want it to be a fun exercise. So make sure you choose a data set which is something that you are really interested in. And the other announcement is about, it's not an announcement actually, it's just a continuation of the project. So make sure you turn in your first part of the project on time. And the reason we are doing that is to ensure that everybody kind of starts in early. In our project one, I saw, at least I noticed a lot of people waited till the last minute to turn it in, were not able to knit their PDF. So this time, make sure you do that step first. So make sure you have everything running. Okay. So don't wait till the last minute to make sure that, to run your code or to run your analysis or to choose your data set. So make sure you have a data set by 16th and make sure you're able to knit your PDF. Okay. This time it will be slightly harder to debug because we cannot meet in person, but my office hours still remain. If you are facing issues, we can share your screen and we can go over it together. But please make sure you do it early, because don't wait till the last minute. Okay. All right, that's it from my side. I'll take any questions that you have. Otherwise, you're free to go.